talk about climate change, we usually focus on the air, rising carbon dioxide, warming temperatures, and the changing weather. But the atmosphere isn't handling this alone. The ocean is quietly doing a huge amount of work. So far, it has absorbed roughly a third of the carbon dioxide we as humans have released, and most of the excess heat trapped by greenhouse gases. That buffering has slowed warming on land and bought us time, but chemistry has consequences. Today we're going to talk about ocean acidification, the direct chemical link between the atmosphere and the sea. We'll look at why oceans naturally absorb carbon, what happens when that carbon dioxide dissolves in seawater, and how small changes in chemistry can make it harder for corals and shell-building organisms to survive. Welcome to the podcast. I'm Dr. Mack, and this is the Climate Translation. In earlier episodes, we've talked about the ocean as a sponge, soaking things up. That's useful, but for ocean acidification, there's a better analogy. Think of the ocean as a giant soda bottle. When carbon dioxide in the air touches the ocean surface, some of it dissolves into the water. That happens naturally, all the time, because gases tend to move from places where they're concentrated to places where they're less concentrated. Right now, there's a lot more carbon dioxide in the atmosphere than there used to be, so more of it is moving into the ocean. That process is called air-sea gas exchange, and it's one of the reasons the oceans is such an effective carbon sink. Wind, waves, and mixing constantly expose new surface water to the air, giving carbon dioxide plenty of opportunities to dissolve. Once carbon dioxide enters seawater, something important happens. It doesn't just sit there as a gas. It reacts with water molecules to form a weak acid we call carbonic acid. This is the same basic chemistry that gives soda its fizz. When you open a bottle of soda, carbon dioxide escapes as bubbles. But when it's sealed, that carbon dioxide is dissolved in the liquid, changing its chemistry slightly. In a very real sense, we're slowly carbonating the world's oceans. Now, the word acid tends to raise alarm bells, so let's be a little more precise. The ocean is not turning into an acid. Seawater is still slightly basic, but what's changing is the balance of chemicals dissolved in it. Since the beginning of the Industrial Revolution, the average acidity of the ocean has increased by about 30%. On the pH scale, that shows up as a very relatively small change, but chemistry doesn't work in straight lines. Each step on the pH scale represents a large change in the amount of hydrogen ion concentration. So a small shift in pH corresponds to a much bigger shift in how water behaves chemically. So students often ask me, if the ocean is absorbing carbon, why hasn't it leveled off? It's because the ocean and the atmosphere are constantly rebalancing. As long as the atmospheric carbon dioxide keeps rising, the ocean keeps taking in more. It's following the rules of physics and chemistry, and that buffering has a real benefit for us. By absorbing carbon dioxide, the ocean has slowed the rate of warming in the atmosphere. Without it, climate change on land would likely be happening much faster. But there's no free lunch when it comes to chemistry. When the ocean absorbs carbon dioxide, it pays a price internally through chemical change. And that brings us to the next step in the story. Because once carbon dioxide becomes carbonic acid, it starts interacting with other chemicals in seawater, especially the ones that marine organisms rely on to build their shells and their skeletons. Coral reefs are often called cities in the sea. They cover less than 1% of the ocean floor, yet they support about 25% of all the marine life. Fish shelter there, invertebrates grow there, entire food webs depend on the complex structures corals build. But those cities are now facing a 1-2 punch. And the important thing to understand is that these punches come from two different directions. So let's talk about heat. Corals are animals, but they don't live alone. Inside their tissues live microscopic algae called zooxanthellae. These algae use sunlight to make food through photosynthesis, and they share that energy with the coral. In return, the coral gives the algae shelter and nutrients. It's a tight partnership, and it's why coral reefs can grow in clear, nutrient-poor tropical waters. Most of the coral's energy comes from that algae. When ocean temperatures rise even a degree or two above normal for long enough, that partnership begins to break down. The coral becomes stressed and they expel their algae. Without the algae, the coral loses both its color and its primary food source. So what's left behind is the white calcium carbonate skeleton, a process we call coral bleaching. A bleached coral isn't dead just yet, but it's starving. And if temperatures return to normal quickly, the algae can come back. But if the heat lasts too long, the coral dies. This is a part of the story most people have heard, but heat is only the first punch. Even if a coral survives bleaching, it still has to build and maintain its skeleton, and that's where ocean acidification comes in. Corals build their skeletons from calcium carbonate using carbonate ions dissolved in seawater as their raw material. Those carbonate ions are the bricks of the reef. When carbon dioxide dissolves into the ocean and forms carbonic acid, it changes the balance of chemicals in the water. Some of the carbonate ions get tied up in reactions that make them unavailable for building skeletons. The result is that corals grow more slowly. Their skeletons become thinner and more brittle. In extreme cases, parts of the reef can even dissolve. And I often get students asking me, well, if corals have survived past climate changes, why is it different this time around? It's because now corals are being hit twice at the same time, and on a much faster timeline. Heat attacks the coral's energy supply. Acidification attacks its structural integrity. It's like trying to recover from a high fever while also suffering from severe osteoporosis. Even if you survive the illness, your bones aren't strong enough to support you. That combination makes recovery much harder. Reefs that bleach repeatedly don't have time to regrow. Reefs growing in acidic water struggle to rebuild even after temperatures cool. Storms and waves cause more damage because the skeletons are weaker, and the consequences ripple outward. Weaker reefs protect coastlines less effectively from waves and storm surge. Fisheries decline. Tourism suffers. Communities that depend on reefs for food and income feel the loss directly. This is why scientists say ocean acidification is not a future problem. It's happening now, quietly, chemically, and in ways that don't show up on satellite images. Corals aren't just responding to warmer water, they're responding to a fundamental shift in the chemistry of the ocean that they evolved in. Now, at this point, let's discuss a way to break this down and make the science more understandable. There's a great way to visualize the ocean acidification process and its impact on corals in your very own home. And it is an experiment I have conducted in the classroom many times. And all it takes is some vinegar and some sticks of white blackboard chalk that you can get from the grocery store. White chalk is made of calcium carbonate. It's the same basic material corals use to build their skeletons. What you do is break the chalk into some pieces and get a clear glass. Add the vinegar to the glass, about halfway, and then drop a piece of chalk into the glass. Almost immediately, you should see bubbles beginning to form. The chalk starts to fizz and slowly dissolve. What you're watching is chemistry in action. The acid in the vinegar is reacting with the calcium carbonate, breaking it down, and in the process, releasing carbon dioxide gas. Now, while this is a great visual, let's be clear. The ocean is not turning into vinegar. Seawater is still mildly basic on the pH scale, not acidic. But ocean acidification is about the direction, not the extreme. As more carbon dioxide dissolves in the ocean, the chemistry shifts. The water doesn't suddenly dissolve the coral, but it does make it harder for corals to build and maintain their skeletons. So, a student might ask me, why don't corals dissolve like the chalk just did? Because the ocean is a much weaker solution than vinegar. But even small chemical changes matter when organisms are trying to build delicate structures, molecule by molecule. It's like trying to build a brick wall while someone keeps taking bricks out of the pile. The wall doesn't collapse instantly, but it does get weaker over time. And that's the part that people often miss. Ocean acidification isn't a dramatic process, and a lot of times it's not obvious. You can't see pH change from space. You can't point to a single event or place in the ocean and say, with certainty, that that was due to only ocean acidification. It's because it works quietly, molecule by molecule, and there are a lot of interactions. But there are places where the effects show up sooner, places that act like natural warning lights. And one of those places is the Great Barrier Reef. The Great Barrier Reef is located in the Coral Sea, off the northeastern coast of Queensland, Australia. It stretches over 2,300 kilometers. That's about 1,400 miles. From the tip of Cape York Peninsula in the north down to Bundaberg in the south. Long-term monitoring in this area has shown that corals are growing more slowly than they did even a decade ago. Even when reefs survive bleaching events, their recovery is weaker. Skeletons are thinner. Breakage from storms are more common. Another set of early warning sites are regions with natural upwelling, like the Pacific coast of North America. In places such as the Pacific Northwest, Washington, Oregon, Northern California, deep ocean water, already rich in carbon dioxide, rises to the surface. As atmospheric carbon dioxide increases, that upwelled water starts to be closer to the chemical threshold that makes shell building difficult. That's why oyster hatcheries in Washington were the first industry to feel acidification directly. Larval oysters struggle to form shells, sometimes failing entirely unless water chemistry was carefully adjusted. So why do we notice it there first? It's because the regions are like stress tests. They experience naturally lower pH conditions, so even small global changes push them past biological limits sooner. These places aren't anomalies, they're previews. So what do scientists do when chemistry itself is changing? Well, the first step is measurement. Researchers deploy sensors on reefs, buoys, and seafloor platforms to track pH, carbonate availability, and temperature all together. Acidification doesn't act alone. It interacts with heat, oxygen levels, and nutrient cycles. So next comes biological research. Some coral species and shellfish populations show slightly higher tolerance to lower pH. Scientists are studying whether selective breeding, assisted evolution, or microbiome manipulation can help vulnerable species survive longer. But there's a reality check here. Those approaches don't stop acidification. They just buy some time. There are also local mitigation strategies. Reducing pollution and nutrient runoff helps reefs cope with stress. Protecting seagrass meadows and mangroves can locally absorb carbon dioxide, slightly buffering nearby waters. In hatcheries, water chemistry can be adjusted during critical life stages. All of this can help, but none of it obviously replaces the root cause. Ocean acidification is driven by carbon dioxide in the atmosphere. As long as atmospheric carbon dioxide rises, the oceans will continue to absorb it, and the chemistry will continue to change. This is why scientists are so clear on one point. There is no technological fix that reverses ocean acidification at scale without reducing carbon dioxide emissions. You can protect ecosystems. You can support resilience. You can slow damage locally. But chemistry follows physics. And that brings us back to why ocean acidification matters so much. It's not just about the corals. It's about recognizing that the ocean is responding exactly as expected to the carbon we've added to the atmosphere, and understanding that response helps us to see where the limits of adaptation lie. The ocean is a life support system of our planet. It regulates climate, feeds billions of people, and quietly absorbs the consequences of what we put into the atmosphere. And right now, it's doing exactly what chemistry says it should, taking in carbon dioxide and changing in response. Understanding ocean acidification helps us see climate change more clearly. This isn't just a story about hotter days or rising seas. It's about balance. It's about the chemistry that allows corals to build reefs, shellfish to grow, and the entire food web to exist. What makes ocean acidification so important and so unsettling is that it's largely invisible. It doesn't announce itself with a single disaster. It works quietly, molecule by molecule, until systems that evolved under stable conditions start to struggle. But understanding that process gives us something powerful. It replaces confusion with clarity. It replaces argument with evidence. And it reminds us that the atmosphere and the ocean aren't separate problems. They're part of the same system. So the ocean is responding, and how it responds depends on the choices we make above the surface. I'm Dr. Mack, and this has been the Climate Translation. If you have a question about the climate that you've been too afraid to ask, or if you have a differing opinion, please let me know. I can use your viewpoints in future episodes. You can reach me at theclimatetranslation@gmail.com. I'll see you next time.